Hello students. In today's class we shall be discussing something about the de Broglie's wave particle duality. We have already learned something about electromagnetic radiations in the previous classes of this chapter. We all know that electromagnetic radiations exhibit a dual nature. According to electromagnetic theory of radiations, the radiations are supposed to have a wave nature. Means electromagnetic radiations propagate as waves, and since they propagate as a wave, they exhibit wave properties like wavelength, frequency, amplitude, etc. But we also know that there are many observations which cannot be explained based on wave nature of radiation. Properties like black body radiation or photoelectric effect, they are explained by giving electromagnetic radiations a particulate nature, means the electromagnetic radiations are made up of particles. These particles which make up radiations are called photons. Thus I can say that photons have momentum because of their particulate nature, and they also have wavelength, frequency, that is because of their wave nature. That is what de Broglie principle states. The principle states that any material particle like photon must exhibit a dual nature. Try to understand. Photon, being a material particle, also exhibits a wave nature. Now, universe is not going to follow different rules for different kinds of particles. So if photon being a particle exhibits a wave nature, therefore any material particle must exhibit wave nature just like photon. So if we extend the dual nature of photon to every other material particle, we get what we call as the de Broglie's principle. Let us see what it states. The French scientist de Broglie in 1924 proposed that any matter like radiation should also exhibit dual behavior, that is both particle as well as wave-like properties. This means that just as photon has momentum as well as wavelength, electron or any other material particle for that matter should also have both momentum as well as wavelength. Such waves which are associated with material particles are called material waves. De Broglie gave an expression to calculate the wavelength of all such material waves. To understand how do we express the wavelength of material waves, let us take example of a material particle like a photon. We have already learnt that for a material particle like a photon, the energy can be expressed as E is equal to h nu according to Planck's quantum theory, where nu is the frequency of the radiation. But we also have a wave equation that states that nu is equal to c by lambda. Therefore, if I replace the value of nu as c by lambda, the energy can now be expressed as E is equal to hc by lambda. Let us give this as equation number 1. According to famous Einstein's equation, the energy of any material particle can be expressed as E is equal to mc square. Since we are talking about a photon which travels as the speed of light, here the velocity c is the velocity of light. For any other particle which is traveling with velocity v, I can write the same equation as mv square. Here I now have two different expressions of energy in form of equation number 1 and equation number 2. Suppose if I equate these two expressions of energy, I can therefore write that hc by lambda is equal to mc square. C on both the sides is going to get cancelled out, and the expression can now be expressed in terms of lambda. If this expression is expressed in terms of lambda, I can now say that lambda is equal to h by mc. But since mass m and c velocity, the product of these two is the momentum, I can therefore say that wavelength of any material particle can be expressed as h by p. How interesting is this equation? See, lambda here is expressing the wavelength, which is the property of a wave, and momentum p here is the property of a material particle. Therefore, this is a beautiful equation that is actually relating the wave-like behavior to the particulate behavior. Understand that momentum can be possessed only by material particles, and wavelength is for the waves. So in other words, the wavelength here, lambda, is the wavelength of a material particle having momentum p. If I extend the same analogy of photon that you just saw to any other material particle, I can therefore say that for any material particle of mass m, which is moving with velocity v, the material wave, or what we call as the de Broglie wave associated with it, can now be expressed as lambda is equal to h by m times v. We all know h here is the Planck's constant, m is the mass of that material particle, v is the velocity with which it is moving. Therefore, it can also be expressed as h by p. A very interesting conclusion that you can get from this particular expression is that the wavelength of any material particle is inversely proportional to its momentum. Therefore, for macroscopic objects or massive objects, since they are massive or macroscopic, they are going to have high momentum. The reason is because momentum is m times v. For those objects which have great mass, they obviously also would have high momentum. So, since macroscopic bodies have a very high momentum, the wave nature that is associated with them becomes insignificant. Let us try to understand this very important thing with help of an example that is going to make it very clear to you. So let us now try to calculate the wavelength of a ball that is having a mass of 0.1 kg and is moving with a velocity of 10 meters per second. Now, do you see this ball moving as a wave? I may sound very stupid to you. How can a ball be moving like a wave? When we throw a ball, we always see the ball moving as a particle rather than a wave. The reason is because a ball can be considered a macroscopic body. Since it is macroscopic, its momentum is large. And for those bodies with large momentum, the wavelengths associated with them are so small that they can be considered negligible. The explanation here is going to make the things very clear to you. So for a ball which is moving with velocity of 10 meters per second, the wavelength associated with it according to the de Broglie's equation can be expressed as h by mv. Now I'm going to substitute the values of h, m and v in this particular equation. H being Planck's constant, we know the value is 6.626 into 10 to the power minus 34 joule seconds. The mass of the ball, which is 0.1 kg, and the velocity, that is 10 meters per second. 0.1 times 10 is equal to 1. Therefore, the wavelength associated with this ball is 6.626 into 10 to the power minus 34 meters. To give you an idea, the size of the atom is estimated to be about 10 to the power minus 10 meters. Means the wavelength associated with this ball is even smaller than the size of an atom. These are so small wavelengths that they can never be experimentally detected. And remember, this was a ball just of a mass of 0.1 kg. For bodies which are even more massive, the wavelengths would still become more and more insignificant. Thus, we conclude that the wavelengths associated with ordinary objects are so short because of their mass that their wave properties cannot be detected. This is the reason why, when you throw a ball, you see the ball moving like a particle and not like a wave. But what about subatomic particles like electrons? They are not as massive as macroscopic objects. So let us try to calculate the wavelength associated with a moving electron. For this, we will need mass of an electron, which is 9.1 into 10 to the power minus 31 kg, and let us say the electron moves at a velocity of 1000 meters per second. The wavelength associated with it, lambda, should now be expressed as h upon mv according to de Broglie's principle. Substituting the values of h, m and v in the equation, I will have lambda is equal to 6.626 into 10 to the power minus 34 divided by the mass of the electron 9.1 into 10 to the power minus 31 multiplied by its velocity, which is 10 to the power 3 meters per second. When I solve this, the wavelength that I get is 728.1 nanometers. This is quite an appreciable wavelength. It is a wavelength that can be experimentally detected. It means that for microscopic particles or subatomic particles like electrons, the wave nature is quite significant. This was one of the major drawbacks of the Bohr's model. Bohr's model completely ignores the wave nature of electrons. To give you evidence about the wave nature of electron, let us look at one very interesting thing. Bohr in his postulate stated that the angular momentum of electron is always quantized, means that electrons can revolve only in those orbits where their angular momentum mvr is an integral multiple of h upon 2 pi. If I want to explain you that why only such orbits are allowed where the angular momentum becomes an integral multiple of h upon 2 pi, I will have to take into account the wave nature of electron. Let us try to understand this with one example. As you can see here in figure number 1, I've got some strings having length L. Suppose if I create a wave on the string, then the length of the string L should always remain an integral multiple of the possible wavelengths. For example, on the first string, I create a wave wherein a single wavelength is equal to the length of the string. On the second string, I can now create a wave wherein two wavelengths are equal to the length of the string. On the third string, I can create a wave wherein three wavelengths are equal to the length of the string. So, in a similar way, if electron as a wave is moving in a circular path, then the length of the circular path, that is its circumference 2 pi r, should always be an integral multiple of the possible wavelength. So, first wave, second wave, third wave, fourth wave, fifth wave, and so on. And when I complete the circumference 2 pi r, I should get an integral multiple of the possible wavelength of electron wave lambda. So according to de Broglie's principle, the circumference of an Bohr's orbit, what you saw here, that was 2 pi r, the circumference of the Bohr's orbit, should always be an integral multiple of wavelength of an electron wave. That is 2 pi r should always be equal to n times lambda. But we know that for any material particle like an electron, the wavelength lambda is h by mv. Therefore, I can say that 2 pi r should be equal to n times h upon mv. I'll take mv on the other side and I'll take 2 pi r down in the denominator on the other side. And I will therefore have mvr is equal to nh by 2 pi. Thus, by considering electron wave, I am able to prove the Bohr's postulate that why only those orbits are allowed wherein the angular momentum mvr of an electron is an integral multiple of h upon 2 pi. Today, we have understood that the wave particle duality is not only about photon, but this wave particle duality can in fact be extended to any other material particle. All material particles in motion possess wave nature associated with them, but such waves associated with macroscopic objects cannot be determined because they are extremely short. But in case of microscopic objects, subatomic particles like electrons, the wave nature becomes quite significant. Therefore, we need an atomic model that also takes into account the wave nature of electrons. That's all for the today's class. I'll see you all very soon with another lecture that is on Heisenberg's uncertainty principle.